Welcome to the fourth video in the rotation topic. In this video, we will be looking at rotational inertia and the kinetic energy. We know that the kinetic energy is defined as half mv squared. So if we have a look at a rotating object, so we say in this case we've got a rotating disk. So it's a rigid object and it's rotating about its axis of rotation in the origin of the coordinate system. Looking at some point near the center, that point is moving with a tangential velocity of v1. For a point slightly further out, that's moving, again, it's got a tangential velocity, we'll call it v2. It has a greater distance to travel in its circle around the axis of rotation. So v2 is greater than v1. And so on and so forth, all the way out to the edge of our disk. So when we're calculating the kinetic energy of an object like this, where we've got different points with different masses and different velocities, we calculate the total kinetic energy just by summing the kinetic energy of each of those little particles. So that means that the total kinetic energy of a system of particles is equal to half times the sum of mv squared. And we sum that over all of the particles in the system. In this case, we sum that over all of the particles in our rigid body. Looking now for the kinetic energy in terms of our rotational variables, we know that our tangential velocity v is equal to r omega, so we substitute that in. We know that each of those particles must make a complete circuit or a complete rotation in the same time period because it's a rigid body. So each of those particles must travel 2 pi radians in the same time period. So that means our angular velocity is the same for all parts of the rigid body. So when we take that into account, we find that our kinetic energy is equal to omega squared on 2 times the sum of mr squared for each particle in the system. And this component, this mr squared, we call this the rotational inertia, I. And so if we substitute that back into our equation for the kinetic energy, we get that the kinetic energy for a rotating body is equal to half times I omega squared. This is the analogous equation to our half mv squared for translational motion, where rather than using the mass of the system, we use the inertia. And this is the biggest difference between when we're working in translational motion and we're working in rotational motion. So the rotational inertia we have just defined as I is equal to the sum of mr squared. So from this equation, we can see that our rotational inertia, it depends on the mass, but it also depends on the position of the mass. So that is, our rotational inertia depends on our mass distribution within our object. And we are already familiar with the concept. So if we imagine a wooden softball bat that's thinner at one end where it's held and thicker at the end that contacts the ball, and we have a wooden rod of the same mass but of a uniform density, and if we imagine spinning the rod, so holding the rod on one end and spinning it in our hand, and doing the same with the softball bat, we find that the softball bat is harder, it requires more energy from us to start it spinning, and it's harder to stop. And if we consider the distribution of mass in each of those objects, in the softball bat, most of the mass is at a larger radius from our axis of rotation, so from our hand. So the rotational inertia of the softball bat is going to be larger than that of the rod. So essentially, if we have an object that's harder to start or harder to stop, it has more rotational inertia. So now we'll look at how to calculate the rotational inertia for two cases. So the first case is when we have a system with a discrete number of masses. So for example, the only system that I could think of, if we have a necklace with a number of beads on it attached by a massless inextensible string, and we hold that by the first bead and we spin it. To calculate the rotational inertia of that system, because we've only got a small number of discrete masses, we simply sum them. For something with a continuous mass, so for example, if we were looking at our Earth and we wanted to calculate the rotational inertia of our Earth, we integrate. So we turn our sum into an integral integrated over the mass dm. And so if we take this formula and we apply it to a number of different rigid solid shapes, we find standard formulas for the rotational inertia. So this table I have unashamedly copied from opentextbc.ca, but you will find a similar, if not exactly the same, with a slightly different colour table in your course textbook. And with that, I'll leave you with the first question under the video, which is to derive the formula for the rotational inertia of a thin rod with uniform density rotating about its centre. So that's the formula I equals ml squared on 12.